So, do we have any questions here? Elena? Oh, sure. So this would be like plus 1989, so I would say like 1991. I forgot to add that number at the end. But to do that, I'm just going to use my calculator and graph and find an intersection. So I'm just going to use the model exactly as they've written. And then I'm going to do 1500 for the other. So the window I used was 0 to 10 because after 10 years I had way more than 1500. And then I did 0 to 2000 because I just needed something bigger than 1500. And then I hit the graph and I get this picture. And to find that intersection, I press second trace and choose the intersect command. So first curve, second curve, and guess gives me 2.06. So when I add it to 1989, I get about 1991. You're welcome. Other questions? Christina, did you have something you wanted to ask about? That was the same thing? Okay. And you're good with that then? Okay. All right. So if there's no further questions, we'll just kind of continue moving on with what we've been talking about.
I thought you were to
Oh, nope, not today.
How about
So we're going to continue talking about logarithms here. So the first thing I want to do is just recap our definition for a logarithm that we saw last time. So remember, this is our definition of a logarithm that we saw from last time. So we'll use this again today, but we're just going to continue talking a bit more about logarithms and a little bit how they work and how to do things. So I want to do now is just talk about some vocab. So there's two situations or special values for b on my logarithm that we're going to give special names and special symbols to. So log base 10 is a special logarithm. We're going to call this the common logarithm. And we're going to use the symbol instead of log base 10. We're just going to write log with no base there at all. So if we write log with no base, we understand the base to be 10. That's all we're saying there. The other special situation is log base e. We call this one the natural logarithm. And we use the symbol ln to represent that logarithm. So if you see ln written, what that means is log base e. So what I want to do next is do a little bit on the calculator and show you how to compute a logarithm using your calculator. So if you have your graphing calculator with you, I'd ask you to take it out because we need to check if we have the command on how to do this with us. Most of you that have a reasonably new graphing calculator will have this command. Some of us, though, we might have to do a different workaround on it if you have an older graphing calculator. So let's do log of 8. So you notice on your calculator on the left-hand side, about halfway down, there's a button that says log on it. That's going to give us the common logarithm. So if I do log of 8, I get this decimal as my answer. And what is this decimal representing? So this is the power of 10 that gives me 8. Let's just kind of confirm that. And that is indeed what we get, right? Is everybody okay there? What if we wanted to do the natural log of 15? Well, if you look at your calculator, you'll notice right under that button that says log is a button that says ln. So I can just type in the natural log of 15, which gives me this decimal. What is that number representing? That's the power of e that gives me 15. Let's just confirm that. So if I go e to the ands, I get 15. Okay. What if I wanted to do log base 2 of 7? The way we can do that is we're going to press the math button and we're going to scroll all the way down until we see the command that says log base. Some of you that have an older version of this graphing calculator might not have this option. Those of you that have your calculators out and are checking, are there any of you that do not have the log base option? Great. Well, that makes life easy. So if I select the log base option, what it allows me to do is go ahead and just type in the values. So log base 2 of 7 gives me this decimal. What does this decimal represent? It's the power of 2 that gives me 7. So if I do 2 to the answer, I get 7. Everybody okay with this idea on how we're using our calculator to get values? Andrew? Should be under the math menu, near the bottom. Not everyone's calculator has that option, though. If you have an older calculator, you might not have that command. You do. If one of you runs into a situation where you find that you do not have that, we can talk again and I can show you how to compute that without that option, but it's a little bit more complicated. Everybody feel okay about using the calculator to get the values, Elena? That allows you to pick the subscript. Just log is base 10. ln is just base e. If I want to be able to pick the base for my logarithm, that's what I'm using the log base command for. Yes. Yes. Okay. The next thing we want to talk about is I want to look at this property. So yesterday we said that exponential functions and logarithmic functions are inverses, right? And we said that f and g are inverses if and only if f compose g of x equals g compose f of x, which is equal to x, right? So let's say I have the function x is equal to log base b of y, and I have the function y equals b to the x. So what I'm going to do here, since this equation is equal to x, I can take this part and plug it into the x in this equation, right? What is that I've just done there? That's composition, right? Where I've plugged one function into another. Composition. So what does that tell me? Well, the only way for me to get y out of this is if this exponent base cancels that logarithmic or logarithm base to give me just y, right? Similarly, we could do the same thing. Since this equation is equal to y, I can take this part and plug it into the y for my logarithm. What is it that I just did there? did a composition again, right? I just did the other direction of the composition. So the only way for this equation to give me x is if log base b and exponent base b cancel. So let's do an example here. So let's say we have 10 to the log of 4. So log of 4 is in the exponent there. Remind me again, when we write log of 4 like that, what's the base for the logarithm? Right? Notice there's no subscript here on my logarithm. Yeah, 10 is the answer. Remember back we defined the common logarithm. We said log base 10, we're just going to write log with no base written there. Okay? So good. What can we do now? Because my exponent base matches my logarithm base, what's going to happen? They cancel, and I'm left with just 4. Let's just check that on our calculator to see that it worked the way that we thought. So if I do 10 to the log of 4, I get exactly that. I get 4. Let's look at another example. What if we have log base 5 of 25 to the x? As this is currently written, can I cancel anything? No. Why not? What's the base of my logarithm? 5. What's the base of my exponential? 25. Those are not the same, right? So the way this is currently written, I can't do anything. However, is there a way for me to rewrite 25 so that it's an exponent with base 5? 5 squared. So I can do that, right? Is everybody okay with what we did there? Now, what I'm going to do is I'm going to look at this part. How do I simplify that? Does anybody remember how to simplify 5 squared to the x? That's correct. So the property of exponents that Annalise used is this power of a power property. And now, if we compare, the base of the logarithm is 5, And the base of my exponential is 5. So what can happen? They can cancel, and we're left with what? 2x is correct. Is everybody okay with this idea? This is maybe the most important concept of this section, is that this exponent base and logarithm base cancel each other out. Okay. Remember yesterday, before we started talking about logarithms, when we were reviewing, we reviewed how to find the inverse of something, right? So let's say we have y equals 6 to the x, and we want to find the inverse for this. What's the first step to finding an inverse? We talked about this yesterday when we reviewed, or the day before, whenever we met last. I guess it wasn't yesterday, was it? I keep saying yesterday. It was yesterday. Okay, well then even better. You should remember then. It wasn't that long ago. So there's 2 steps to doing this. The first step is we want to get the x by itself. So how in this case are we going to get the x by itself? What do we have to get rid of? That's 6, right? Okay. So what can we do to both sides of this equation that's going to cancel out that 6? What? Log base 6. Very good. Right? So we need the logarithm whose base matches the exponential base. So to both sides of my equation, I'm going to do log base 6. Because we know that log base 6 will cancel with exponent base 6. Leaving me with just x on the right-hand side. Is everybody okay with what we did there? All right. So the x is by itself. That's step 1. The second step to finding an inverse, we have to swap the x's and y's. So everywhere there was a y, I'm going to write an x, and everywhere there's an x, I'm going to write a y. And that's it. Is everybody okay there? Good. Let's do another. So let's say we have the equation y equals the natural log of x plus 3. Remind me again, what is the base for the natural log? E. Remember we defined that just a few moments ago. Okay. So what do we need to do to both sides of this equation to cancel out that log base E? We're going to use the exponent base E. Very good. So you notice when I write this out, I'm writing the E in quite an exaggerated fashion because I want to make sure that it's clear that we're not multiplying both sides by E. E is the base and Y is the exponent on the left side. And on the right side, E is the base, and log base E of x plus 3 is the exponent. Very important that you do not confuse that with multiplication. It is not the same thing. Everybody okay? Okay. So what's going to happen here? Log base e will cancel exponent base e. And we're left with e to the y is equal to x plus 3. Again, trying to get x by itself, that's our first step. So is the x by itself right now? No, we still have a little bit more to do. What do we still need to do? Subtract 3 from both sides. And again, 3 is not a common or like term to e to the y, so I'll just write it next to it. And then my last step is to swap the variables. Is everybody okay on this kind of a problem? Again, the main concept or the main takeaway here is that we have to use a logarithm to cancel an exponent base, and we use an exponent base to cancel a logarithm. Everybody's okay with that idea? Okay. The last topic I want to talk about today, and it's kind of a long one, is graphing logarithmic functions. Okay, so just to reiterate, this is like the second or third time we're saying this today, but exponential and logarithmic functions are inverses. So remember, for exponential functions, that looked like this, we have a horizontal asymptote. Does anybody remember how we found the horizontal asymptote for an exponential? It's y equals k. Very good. And then how did we find the domain? Good. It was always all real numbers. And the range was it's everything above the asymptote. And if a is less than 0, it's everything below the asymptote. So our general form for a logarithmic function is y equals a times log base b of x minus h plus k. So remember how we find an inverse in like the most abstract sense is we're just taking our function and switching the x and y coordinates for every point on that function, right? So for an exponential function, we have a horizontal asymptote. If I swap the x and y coordinates on that horizontal asymptote, what's going to happen to it? It's going to become a vertical asymptote, right? So for a logarithmic, we have a vertical asymptote at x equals h. So remember, the domain is about which coordinate, x or y? X. So if I take the domain of the exponential, that's really going to tell me about the range for its inverse, right? Is everybody okay there? And similarly, if I take the range of my exponential, that'll tell me about the domain for my inverse. And because of the situation, we're looking at a little bit of an overly simplified situation here. So there's not two possibilities even for the domain of a logarithmic because of the way that we've written the general form. So we're just going to have vertical asymptote to positive infinity. Won't consider another option. Okay with that idea? So again, trying to connect this back to something we already kind of know about so that it's a little bit easier to remember. So when we make an XY table to graph a logarithmic function, I'm going to pick my x's in a very special way because I don't want to end up with any like irrational numbers for my y. So I'm going to pick my x's in this very special way. So if you look at these x coordinates, what's the only thing that's changing? The exponent on my b, right? So let's just take a look real quick at why choosing our x's this way is going to be really a smart thing to do. So if I take my general logarithmic function and say let's plug in that first value for x. So in place of x, I'm going to plug in b to the negative 2 plus h. Look at what's going to happen here. I have a plus h and a minus h. Those are going to cancel out, right? And then I have a log base b and an exponent base b. Those are going to cancel out. So what are we left with is just negative 2 times a plus k. Isn't that nice? So if I continue this pattern, that'll be how I can find my y coordinates. What do you notice is the only thing that's changing? The coefficient on the a, and notice that that coefficient matches the exponent from the x coordinate. Not by accident. Not by accident. That'll be how it always works. Everybody okay with that? So let's do a concrete example now to make sure we have the hang of it. So let's say we wanted to graph log base 2 of x plus 3 plus 1. The first thing I would do is write down my values for a, b, h, and k. So who can tell me what the value for a is here? 1. Good. Because remember, a is the coefficient on our logarithm. Oops. And since there's no coefficient there, we know that's 1. What's the value for b? 2. What's the value for h? Negative 3. And the value for k is 1. Okay. So what's my vertical asymptote going to be in this situation? It's going to be x equals h, which is -3. Then let's make our xy table. So I'm going to do b to the -2 plus h, b to the -1 plus h, b to the 0 plus h, b to the first plus h, and then b to the second plus h. Now I'm just going to go ahead and evaluate those on my calculator because I would prefer to have a decimal here for graphing purposes. So that gives me -2.75 for my first x coordinate. And if I continue on, I would get those. Now we'll fill in our y coordinates. So I'm going to have -2 times a plus k, -1 times a plus k, 0 times a plus k, 1 times a plus k, and 2 times a plus k. And again, we'll just evaluate these. Everybody's okay to there? Now that I have my XY table, I'm going to go ahead and make an axis. So 1, 2, 3. 1, 1, 2, 3. So the first thing I like to do is draw in my vertical asymptote. So that vertical asymptote's at -3. So I'm going to draw a vertical line that goes through -3. Yes? Sure. Make sure you wash your hands. And then I'm going to plot my points here. So -275 and -1. And then -2.5 and 0. -2 and 1. -1 and 2. And then 1 and 3. So I'm going to go ahead and draw my graph. So I'm going to follow the asymptote, go through all of my points, and I'm going to have arrows at both ends of my graph. Everybody okay with how we've drawn the graph there? Of course. The last thing I'm going to do is write the domain and range. So remember, the domain is the h to positive infinity, and the range is always all real numbers. What do you guys think? Hopefully that doesn't feel too bad. Not much different than the exponential, right? We have a little bit of rules on how to choose our x's and y's, and little rules on how to find our asymptotes and our domain and range. And then it's just about getting it all drawn in correctly. Okay? Let's stop here. We did I would say, a pretty good amount.